Ionic bonding. What is ionic bonding? Ionic bonding is the complete transfer of valence electrons between atoms. It is a type of chemical bond that generates two oppositely charged ions. This is a metal. In ionic bonds, the metal loses electrons to become a positively charged cation, whereas the non-metal accepts those electrons to become a negatively charged anion. Ionic bonds require an electron donor, which is a metal, and an electron acceptor, which is a non-metal. Why ionic bonding? Ionic bonding is observed because metals have few electrons in its outermost orbital. By losing these electrons, these metals can achieve noble gas configuration and satisfy the octet rule. Similarly, non-metals that have close to 8 electrons in its valence shell tend to readily accept electrons to achieve noble gas configuration. In ionic bonding, more than one electron can be donated or received to achieve octet structure. The charge on the anion and cation corresponds to the number of electrons donated or received. In ionic bonds, the net charge of the compound must be zero. Properties of ionic compounds. Ionic compounds have high melting points and high boiling points. Why? High temperatures are required to overcome the attraction between the positive and negative ions in ionic compounds. Therefore, a lot of energy is required to melt ionic compounds or cause them to boil. Ionic compounds are hard and brittle. If you attempt to hammer down on ionic substances, they will shatter. This is very different from metals, which can be hammered into different shapes without the metal atoms separating from each other. Ionic compounds are hard because the positive and negative ions are strongly attracted to each other and difficult to separate. The strong forces in ionic compounds are called electrostatic forces. Ionic compounds conduct electricity when they are dissolved in water. When ionic compounds are dissolved in water, the dissociated ions are free to conduct electric charge through the solution. Molten ionic compounds also conduct electricity. Thus, ionic compounds conduct electricity in liquid or aqueous state. However, ionic solids do not conduct electricity very well because the ions are bound so tightly to each other.
Covalent bonding. Simple covalent compound. They are made up of only non-metals joined together by sharing their electrons. Most covalent compounds have a simple molecular structure. For example, bromine, oxygen, carbon dioxide, and hydrogen. Simple covalent compounds have a low melting and boiling point. Within each molecule, the atoms are held together by strong covalent bonds. However, between these molecules are only weak van der Waals forces holding them together, which can be easily overcome with little energy. Hence, simple covalent compounds have low melting and boiling points and are volatile. Secondly, simple covalent compounds are insoluble in water but soluble in organic solvents. As simple covalent compounds have the same type of intermolecular forces as organic solvents, that is, weak van der Waals forces, therefore, it is easy for non-polar molecules to move between simple covalent molecules. The molecules mix together and the simple molecule compound dissolves in the organic solvent. However, polar molecules attract each other strongly. Weak forces between simple molecules are not strong enough to separate the water molecules. Hence, simple molecular compounds are insoluble in water. Exceptions are sugar and hydrogen chloride, which are soluble in water. Hydrogen chloride can dissociate and form ions when they dissolve in water. Thirdly, simple covalent compounds do not conduct electricity. Simple molecular compounds do not have any free-moving ions or electrons to conduct electricity. Exceptions are hydrogen chloride, sulfur dioxide, and ammonia, which are able to dissolve in water to form solutions that conduct electricity. In summary, simple covalent compounds are low in melting and boiling points, insoluble in water but soluble in organic solvents, and bad conductors of electricity.
Metal atoms contain few electrons in their valence shells relative to their periods or energy levels. The electrons are readily lost, so in metals, positive stable ions are formed. A sea of electrons permeate the lattice, and they are also able to migrate through the lattice when an external electrical field is imposed, leading to electrical conductivity. Metals tend to have high melting and boiling points because of the strength of the electrostatic forces of attraction between the ions and the delocalized electrons, which take a lot of energy to overcome. The strength of the bond varies from metal to metal and depends on the number of electrons it has. Group 1 metals like sodium and potassium have relatively low melting and boiling points, mainly because each atom only has one electron to contribute to the bond. They are relatively large atoms, meaning that the nuclei are some distance from the delocalized electrons, which also weakens the bond. Metals conduct electricity in their solid states. The delocalized electrons are free to move throughout the structure in 3 dimensions. Liquid metals also conduct electricity, showing that although the metal atoms may be free to move, the delocalization of the electrons remain in force until the metal boils. Metals are good conductors of heat. Heat energy is picked up by the electrons as additional kinetic energy. The energy is then transferred throughout the rest of the metal by the moving electrons. Metals are described as malleable, meaning that they can be beaten into sheets, and ductile, meaning that they can be pulled out into wires. This is because of the ability of the layers of atoms to roll over each other into new positions without breaking the metallic bond. If a small stress is put onto the metal, the layers of atoms will start to roll over each other. If the stress is released again, they will fall back to their original positions. Under these circumstances, the metal is said to be elastic. If a larger stress is put on, the atoms roll over each other into a new position, and the metal is permanently changed. This rolling of layers of atoms over each other is hindered by grain boundaries because the rows of atoms are not aligned properly. The more grain boundaries there are, the harder the metal becomes. Offsetting this, because the grain boundaries are areas where the atoms are not in such close contact with each other, metals tend to fracture at grain boundaries. Increasing the number of grain boundaries not only makes the metal harder, but also makes it more brittle. You can break up the regular arrangement of the atoms by inserting atoms of a slightly different size into the structure. Alloys, which is what this is called, such as brass, are harder than the original metals because the irregularity in the structure helps to stop the rows of metal atoms from sliding over each other.
Macromolecular, also known as giant molecular structures, are substances that exist as a giant network of atoms that are covalently bonded. Examples of such include graphite, silicon dioxide, and diamond. Giant molecular structures have a high melting and boiling points, as they consist of large number of atoms that are held together by strong covalent bonds, which would require high amounts of energy to break them. Thus, due to the high melting and boiling points, giant covalent structures tend to be solids in room temperature. They are also unable to conduct electricity with the exception of graphite. as all the outer electrons are used to form covalent bonds. Hence, there are no free electrons that can move around the structure to conduct electricity. Giant molecular structures are also insoluble in water and inorganic solvents, as they are held together by strong covalent bonds, and any forces of attraction between the giant molecular structure and solvent molecules are not strong enough to break the strong covalent bonds. Now, let's investigate the diamond. It has a high melting point and is hard. Each carbon atom is covalently bonded to 4 other carbon atoms, which in turn bonds to another 4 more carbon atoms, forming a 3-dimensional structure, which is thus difficult to break. It also does not conduct electricity, as all the outer electrons are used for bonding and have no free electrons to move through the structure to conduct electricity. Now let's investigate the graphite. It has high melting and boiling points, as each carbon atom is covalently bonded to 3 other carbon atoms, which is in turn bonded to another 3 more carbon atoms, forming a continuous layer of hexagon, which is difficult to break. They are also soft and slippery, as these layers of carbon atoms are held loosely by weak van der Waals forces of attraction and thus will slide over each other when a force is applied. Graphite also conducts electricity, as each carbon atom has 1 outer electron that is not used for covalent bonds. These electrons are able to move freely among the layers from one carbon atom to the next. They are also said to be delocalized. These free-moving electrons will allow the graphite to conduct electricity. Now let's investigate the silicon dioxide. It has a high melting and boiling point, as each silicon atom is bonded to 4 other oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms, which forms a 3-dimensional structure and is thus covalent, and it thus has strong covalent bonds that are difficult to break. It also does not conduct electricity, as all the outer electrons of the oxygen and silicon atoms are used for bonding. Hence, there are no free electrons that can move through the structure to conduct electricity.
Diamond, graphite, silicon dioxide, macromolecule,